Okay, welcome back to our third session of today. So I was just explaining the growth targets in annual terms per annual growth rate of 2% should be converted to 25-year growth rate, and then that growth rate is 64%. Okay, from a period of 25 years ago to today. Okay, so then the growth rate formula and the values of other parameters such as sigma, theta, alpha, eta, and eta allows us to compute gamma. Okay, and gamma would be around 5%. Now we have all the parameters, right? And we can design our experiment. Now suppose that our research question is about how education subsidies increase growth rate. Okay, how education subsidies change welfare level. Okay, and here let's look at a very simple change in education subsidies. So typically our benchmark calibration had this 23% subsidy rate. Okay, and suppose that in the experiment we are increasing the subsidy rate by 5 percentage points. Okay, now we can calculate the growth rate, okay, using this formula. Now you can calculate the new growth rate, right? Because the other parameters are the same, but sigma is equal to 28%. You can also run you can also run the experiment and see how the GDP share of education expenditure changes, how utility changes. Okay, you can do all sorts of things because the model is very simple. One other experiment. Now we can actually, I mean, after the slides, we can actually do that in MATLAB. I'm going to show you some steps, some stuff. So maybe we can also keep sigma at the benchmark, right? Sigma at 23%. But imagine this. Suppose that we use this tax revenue to reformize the education system, okay? So that type of reform would be imagined to increase gamma, okay? Remember what gamma is. Gamma is the overall productivity of the education technology right here, okay? So maybe I can use this tax revenue not to subsidize education spending, but use that money to make a reform, to implement a reform in the education system, so that the purpose of the reform would be to increase the quality of the education system by increasing gamma, okay? So that can also be studied. And then we have two different policies, right? Subsidize education expenditure at a higher rate than 23%, or increase the productivity of the education system. So which policy is better in terms of welfare? Now that's a very good question, right? So suppose, I mean, imagine this for the Turkish economy right now, right? So suppose that government pays some tuitions, right? So there's this tuition waiver. So once you are in the state university, you don't pay any tuition at all. And of course, this is subsidized through the fiscal system, right? Now, instead of doing that, suppose that government actually collects tuitions in state universities, but instead the money is used to reformize the education system, okay? So which policy is really better? Because there is now a limited amount of resources, right? So your resources are constrained. And as a government, you try to understand what would happen if I do alternative, if I experiment with alternative policies, okay? So that type of questions are really, really important. So let me give my final remarks and show you some stuff in MATLAB, right? What we saw here today in these 2 hours is the elementary logic of computational experiment, Okay. And this is particularly designed, I mean, this lecture is particularly designed for the growth economics. So we had this very simple model, and we tried to, you know, apply the Kidman-Prescott methodology to that simple model and with some simple questions, right? In research, so this is the teaching part, right? So in research, if you want to use such stuff, typically model will be, of course, more complicated. Okay, and you will see what I mean by that in a couple of weeks when I show you my 2019 paper. Usually, we want to find a numerical solution. I mean, we are required to find a numerical solution because there is no analytical solution of the model. And most of the time, again, in research, you have to write the numerical algorithm that finds the solution and calibration together. Okay, so these are connected to each other. I mean, it is not always very simple to do the calibration without solving the model and vice versa. In general, it is a hard task to take an endogenous growth model to the data. Okay, even if your model is simple enough, there are some complications when you want to map the model to the data. Okay, the most important stuff is this. Really interesting questions require heterogeneous agents models. Okay, so in that particular simple example we have today, there's no heterogeneity. Every worker is alike, every kid is alike, right? It is not true in reality. In the real world, kids have different talents, right? Some kids are very good at math, some kids are very good at dancing. So how do we account for these differences? Well, we use stochastic models and we use distribution assumptions about unobserved stuff, including innate abilities. All right. So if you want to do that type of research, you learn the new methods and you learn how to apply these new methods. But this is the baseline philosophy. Okay. Question, theory, a particular parameterized model, calibration exercise, and finally the experiment. Okay. In some simple models, you can do some stuff by hand by using pen and paper. In some more interesting models, more interesting questions, you do much of the stuff using a computer. Okay. So let me show you. How can you run this model in MATLAB. So I was just, during the break, I was just compiling this file because you asked for it. So in MATLAB, so this is a simple script. Okay, so okay, of course, I'm not sharing it right now, so you cannot see. Let me share my screen altogether. So this is the main window in MATLAB. Okay, so when you open MATLAB, you see this. So this is mine is 2019 version. So this is the workspace. This is the command window. This is the command history. So workspace is here. So if I define something, oops, if I define something, for instance, it is recorded here, and I can actually use this folder. Let me go to our class folder, for instance. So right here, our file is here. I just, as I said, open this file for today. So when you click on new script button here, an empty file like this opens and you just type your comments, right? Now, what we want to do is to write a simple script that simulates this model. First, we do some cleaning. So this is to clear command window. Okay. This is to clear workspace. And this is to close all figures previously opened, previously generated, let's say. Okay. And as you see, I use the percent symbol for comments. Okay. So 1% symbol in MATLAB is to create a comment. Two symbols creates this section. Okay. Now we set the model horizon to 10 periods. Why? Because this is a long run model, so 10 periods actually mean 250 years. And these are the parameter values. Now remember that we actually have alpha eta parameter, right? Remember what was it equal to? So alpha times eta was equal to this, right? So you have that as alpha eta. Then I told you that you can run the stuff for different values of eta, right? So now I'm creating a vector of different eta values, 0.6 and 0.8. You can do actually even finer, right? 0.3, 0.5, 0.7, right? So this now is a vector. Then what is alpha equal to? Alpha is equal to alpha eta divided by eta, right? So you have alpha divided by eta. Let me double check whether this works. So you go to the command window, you clear all this, and it doesn't work, of course, because this is wrong. It must be alpha eta divided by eta. So let's do it again. Yes, so as you see, you have different values of eta and different values of alpha, right? So you can actually now see different values of alpha and eta. Okay. So in the editor again, one other thing. So if you put this symbol here, that's the convention. So once you put it, it is not appearing in the command window. Now remember what sigma is equal to. Sigma was equal to 23%. Gamma was equal to what? Gamma is equal to 0.049. And theta was equal to some large number, right? Theta is, okay, 12,000. Theta is 12,000. Okay, now the parameters are given, And with different eta parameters, you have different alpha parameters, okay? Now, the initial value of human capital could be assumed to be equal to what? So maybe we can assume this number, right? Because that was the 2002 value from the Penwell table. Now, at this point, let me just save this. So at this point, we want to create an empty report. Okay, empty report for variables. So to do this, I'm going to use that command, not a number. Okay, so not a number, abbreviated in this way. And when I do this, let me show you first. Let's clear all this. So in MATLAB, everything is in matrix form. Okay, so when I write this, for instance, this is a vector, right? A column vector. So when I use these semicolon operator. So when I write without semicolons, it is a row vector. Okay. So to write a matrix, what would you do? So let's write the identity matrix. 1 0 0 1. Right? So row vector and another row vector. Okay? So everything is in matrix form. Even if you define a scalar, right? It is also a matrix. So now what is the size of I, the identity matrix? Now the first element is the row, and the second element is the column number, right? So if I define a matrix with different numbers of columns and rows, so let's suppose that this is 1, 2, 3, and 4, 5, 6. Now this is a matrix with 2 rows and 3 columns, right? So size A1 is the number of rows, okay? And size A2, the second dimension, is the number of columns. Okay. Now, what I do here by creating an empty report, I'm creating the entire time series of education expenditure, but as an empty report, right? So here, I create the education variable for the model horizon of 10 periods, okay? And it is a column vector. The first size is the number of rows, and the second, so the first element here is the number of rows, the second element is the number of columns, okay? So I do this for each and every variable. And I also have GDP per worker, and we have age already. So what do I need? I have consumptions. Yes, I can define utility. Okay. So that will be the utility. Now, what I will do is to assign this value, the initial value, for human capital, right? Because I know in the first period, it will be equal to this initial value, right? And all the model variables will be expressed as functions of this. So here for forward recursion, we will use what we call the for loop. Okay, so this is called a for loop. You will get it when I write it. So now I'm going to solve the model. Now I know that ET is equal to what? Now let's go back to the solution ET. where is it? So ET is equal to that. So I write alpha eta times, divided by 1 plus alpha eta, right? Times theta ht, theta times ht, right? Times 1 over 1 minus sigma. Okay, so that would be ET. Now, how do I know that this works? Because now, for t is equal to 1, right? For t is equal to 1, the computer knows what E11 is, right? Because the computer knows sigma, the computer knows H11 from here, computer knows theta, alpha eta, and alpha eta. Okay, so I know what ET is. I also know what WT is, right? WT was equal to theta times HT, right? And also this is equal to output. This is the simple model. Okay, so these are what I remember. Then there's consumption. Now, careful, consumption will be, okay, first we have tax. Now, government budget constraint tells me that tax will be equal to sigma times ET, right? Remember this from the model. Where is it? So right here, as you see, the tax revenue of the government will be equal to sigma times ET. So it is there. So let's create the tax variable here as well. Tax is equal to number 1, right? So I know the tax, I know the education spending. Now I can write consumption. How do I write consumption? Well, income minus tax minus education spending. And education spending is 1 minus sigma times education, right? So let's double check. Yes, as you see, consumption is equal to WT minus TT minus 1 minus sigma ET. Okay. Then what do I have? We have C, we have U. What is utility equal to? Now, utility will be equal to log CT plus alpha times log HT plus 1. First, we have to compute HT plus 1, of course. Now, HT plus 1 will be equal to gamma times ET to the eta, right? ET to the eta times HT to the 1 minus eta, right? But be careful, we are creating, so this will be log HTT plus 1. Now, here you should be careful because we have here defined different alpha eta values, right? So when I write alpha here, either I'm going to put another loop outside, but instead of doing that, for simply, I'm using a particular value. So alpha, let's do this. So that would be, let's say, eta, that would be alpha. Okay, so that would be eta. So when I write alpha, let's say we are looking at the third value. Okay, so eta would be also equal to the third one. You can later on change this, obviously. Then you have alpha, eta, education, tax, utility, and that's it. N. Okay. Now, when you run this, it will run smoothly, I believe. So there's no problem as far as I see. So you can now plot it. Okay, so let's plot log GDP per worker. Okay, so now I'm saving it, and now I'm running it, and we see whether it works. Oops, it worked, but for some reason it is decreasing. So there is a problem with there's a problem somewhere, I believe. So let's try to find it. Data. So the growth rate, I guess, is, so what's the problem here? Log Y. Okay, I cannot see it. What about the education spending? Okay, so the model does not have growth under this parameterization. Let's increase sigma a little bit. Let's say, let's do this. No, it continues. Okay. All right, there's a problem here that I cannot see right now. Is it because the horizon? It shouldn't be. No, it is not. I'm not surprised. So there is I think it is the value of growth rate. Right now I cannot see it. So the growth rate is equal to where? Where's the growth rate? So possibly the growth rate is less than 1. That's the problem. Okay, so the growth rate is, so to write the growth rate in the economy, I have to write GT.
Hocam.
Yeah.
En üstte sigma'ya siga yazmışız. Başka yerde sigma yazdıysak.
Yok. Ben hep siga yazıyorum.
Redefine
Ha, tamam.
siga.
Tamam.
So let me define the growth rate here. Okay. So HT plus 1 divided by HT minus 1, right? So let's look at the growth rate. If I run it, yes, the growth rate is so small and it's actually negative. So how do we increase that? We have to increase gamma. So possibly I have a mistake there. So in one of these equations that I calculate gamma, I think I have a particular error. Okay, that equation could be erroneously calculated. But if I increase gamma, let's say I do it, let's say it is equal to 1%, 10%. Let's run it now. Okay, not good enough. 50%. Okay, that's too much. 15%. okay, G is, so what I want is 2%, right? So this is now, so, you know, no, G must be 64. So let's do this. 2%, also 20%, okay. So there is a value, okay, I'm getting close as you see. Okay, 64, so maybe it's like something like this. Okay, so good enough. Right, okay, 64. Now, as you see, if I calculated gamma correctly in the slides, so that would give me a growth rate that is roughly fixed, as you see. So if you look at the solution here, where's gamma G? So G is here, and it is very close to that number, right? So there's almost no fluctuation. So there's some numerical discrepancy, which is normal. But let's look at the GDP per worker. It's low, obviously. So when I run it, now as you see, log GDP grows, right? So log GDP is linear. This means GDP grows at an exponential rate. Okay. Now you can tell me, now you can save it actually. How do you save it? Well, save. So first you create the variable. Let's say this is benchmark. Okay, so benchmark is equal to E by, let's say, okay, E by CU. So you have save benchmark.mat. Mat is the file extension for MATLAB files and benchmark. So when I do that, you're gonna have, as you see, BM mat, right? So that was not there before. So let's clear it and let's load benchmark data that I just run. Oops, obviously I have to use these. So when I load, oops, oh, not dot, of course, it will be mat, right? So as you see, the benchmark data is here, right?
Less than 1 minute we have.
All right. Okay. Let's meet at 11:50. Okay. 11:50
Okay.
to conclude.
Okay.
All right. Bye bye.